The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. My name is Eden Reed, and I'm the Senior Marketing Associate here at RheoSense. I wanted to just welcome you all to our November webinar. This is our Tools of the Trade. Why can't I get all the viscosity measurements I want with just one tool? And we are proud to introduce our two hosts for today's webinar. We have Principal Scientist Dr. Stacy Elliott and Research Scientist Dr. Zachary Imam. Both Dr. Elliott and Dr. Imam oversee the RheoSense research and development team. They have a shared passion for rheology and a scientific curiosity that drives new and innovative viscosity applications here at RheoSense. Dr. Elliott obtained her extensive experience and rheological knowledge through her education at Carnegie Mellon University and Princeton, as well as her experience at both Alcon and DuPont. Dr. Zachary Imam obtained his PhD in biomedical engineering from the University of Texas at Austin and spent a year postdoctoral continuing development on bioscience project funded by the Department of Energy's Basic Energy Science Program, studying the biophysical properties and functions of microtubules. So I am very pleased and honored to introduce to you all both Dr. Elliott and Dr. Imam to go ahead and present to you Tools of the Trade.
Thanks for the introduction, Eden. This is Zachary, and today we'll be talking to you about why you can't just use one tool for collecting your viscosity data. And this is actually a question that we get a lot about our instrumentation, but this is also true for other types of instrumentation like rotational rheometers or even capillary rheometers. There's a specific range of tools used for specific samples, and it's 100% dependent on the viscosity of your sample and the shear rates that you want to test your samples at. So we're just going to show you why that is, derive why that is, and hopefully clear up some confusion on which tools are appropriate when and where, and how that translates to your experiments with your fluids. And to start things off, I'd like to bring an example that many of us are familiar with, cooking. So especially with at least those of us in the United States, we have a big holiday coming up next week that involves a lot of cooking. And you will probably be using one of these tools or multiple of these tools during your cooking. And so specifically knives. And so as many of you are familiar with, there are multiple different kinds of knives depending on whatever application you're going to be using with said knife. So we have bread knives that are ideal for cutting bread, but maybe not the best tool for, say, cutting meat or chopping vegetables. We have butter knives, which are good at cutting butter, but not much else. We have carving knives for your Thanksgiving ham, which are ideal for carving the meat. And we have also cleavers for butchering and chef's knives for chopping vegetables and meat. Like, we have a bunch of tools at our disposal, and some of them are better at certain jobs than others. And this holds true for rheology. So I'll begin by talking about our specific instrumentation, the VROC technology, Viscometer-Rheometer-on-a-Chip, which is a microfluidic platform that uses MIM sensors, and where we flow fluid through our rectangular slit channel, and that fluid then compresses capacitors or pressure sensors, which then correlate to a pressure drop as the fluid passes through the microfluidic chip. And we can use this pressure drop, this slope, or the derivative of this pressure drop to then measure the shear stress of your fluid. And then, since we control the shear rate or the flow rate through our rectangular channel, and we know the geometry of the channel, we can then calculate the shear rate. So then we get our shear stress divided by shear rate, which is your dynamic viscosity. And this principle holds true throughout all of our instruments, whether it's the Microvisc, MVROC, or Initium 1 Plus. And for the purposes of this webinar, I'll be talking more from the perspective of the Initium 1 Plus, but this kind of approach is true for all of our instruments. So first, when you're deciding which chip to use, so what varies between our instrumentation really is which chip you're using. So we have A chips, B chips, C chips, and E chips, and I'll go into detail about those chips and the differences in a couple of slides. But we can use different kinds of chips with different kinds of flow channels to then guide which instruments we use or which experiments we run. But the first question you need to ask yourself is, what kind of experiment do I want to perform? Am I running a shear rate sweep? Am I measuring my fluid over several different shear rates? Am I doing a temperature sweep where I'm keeping the shear rate constant and I'm changing the temperature to see how the viscosity changes with temperature? Or am I performing an intrinsic viscosity measurement where I'm using very low viscosity samples and very dilute solutes within the solvents that we're using? Knowing this information up front will help you decide which kind of chip you're going to use in your experimentation, because just like the knives from my earlier example, the different kinds of chips are ideal for different kinds of experiments. And so here we have our 4 chip varieties that are on the Initium 1 Plus, but these 4 chip varieties also can be used on our Microvisc and VROC platforms. The Microvisc and VROC have actually more channel depths. So they have, the channel depth dictates what your shear rate range is. So, but the letter, the A, B, C, and E, corresponds to the pressure range that the chips can withstand. So A chips are the lowest pressure chip, E chips are the highest pressure chip, and B and C are along the middle. B chips are closer to A chips. C chips overlap with both the B chips and the E chips, so on and so forth. And so the letter corresponds to the maximum pressure that the chip can withstand, and the minimum pressure of all our chips is 5% of the maximum pressure. And this is just so that we can get a strong signal to noise ratio so that we're confident in our shear stress measurement. And so if you look at the table below, you can see that on the 1 Plus platform, the A05 chip has a range between 600 and 12,000 pascals, the B chip 1,600 to 40,000, C 10,000 to 200,000, and the E chip 72,000 to 1.8 million pascals. And again, if you look at the final column in the table, you can see that the shear rates for the A05, B05, and C05 are the same, and that's because the shear rate range is dictated by the channel depth size. And then the E chip has the smallest channel depth, which is 20 microns, and it has the highest range of shear rates that it can explore. And so to answer the big question, why can't I just use one chip for everything? It's because chips need the viscosity of the fluid and the shear rate in balance. And so what that means is the pressure that the chip withstands is a combination of both the viscosity of the fluid and the shear rate that you are shearing the fluid at. Both of these together, if you increase the viscosity of the sample, you also increase the pressure that the chip is experiencing. And likewise, if you have a high shear rate through the chip, you're also introducing a lot of pressure. So it's the combination of the viscosity of the fluid as well as the shear rate that dictates what kind of pressures the chip experiences. And so for the case of the Initium 1 Plus, the A05 chip is really ideal for low viscosity fluids, less than 2 centipoise, and is really powerful at using as a tool for measuring the intrinsic viscosity, because it can get a really, really high signal to noise ratio with these really low viscosities. And so that is good when you're trying to use these, when you're trying to measure intrinsic viscosity of your samples. The B05 chip I like to call the jack of all trades, master of none. It can do a whole lot of different experiments. It can do intrinsic viscosity depending on the sample, but it's not ideal. You can do it, but it's not perfect at it. Likewise, it can reach high shear rates depending on the sample that you use, but again, it's sample dependent, and it can, in some cases, can't reach shear rates where you will get to see interesting rheology, like shear thinning, for example. And then the C chip is kind of like a more powerful B chip in that it can handle more high viscosity fluids and lower shear rates, but unfortunately, if you have a low viscosity fluid, it can't reach the signal to noise ratio with low viscosity fluids like the B chip can, so it'll miss some data as well. And then the E02 chip is good at high viscosity, high shear. It can achieve the highest shear rates on the OnePlus platform, but it can't really handle low shear and low viscosity samples. And so down here on the bottom, I kind of have a visualization so you can see how the different chips overlap with each other. And so, for instance, if you wanted to do a big experiment over multiple shear rates over the longest or the widest range of shear rates, you would then choose a sample where you could run it on the B chip and you have a wide range of shear rates it can explore. Then a C chip, which will have a little bit of overlap with the B chip range, and then an E chip where you have a broader range and it overlaps well with the C chip but not the B chip, so on and so forth. And so we also have tools that we can use to then choose a shear rate. We have this interactive protocol development spreadsheet that we can share with our customers where you input the chip parameters and then your sample parameters, and then you can then build your own shear rate sweep or temperature sweep depending on the sample, and let it guide you towards what experiments that you want to run on your samples. And so you have the chip summary information here. You can input that in the chip information tab in this spreadsheet and then input your sample information. And I have a screenshot of this exact spreadsheet in a later slide, and it'll make more sense when we get to it. And so if you're completely in the dark, you can kind of gauge which chip is appropriate for your sample, and by estimating the kind of pressures you will experience within the instrument with your specific sample. So on the Initium One Plus, the minimum flow rate is 2 microliters per minute. The maximum flow rate is 1,200 microliters per minute. And for the two different channel depths, that corresponds to 20 micron. For the 20 micron flow channel depth, the EO2 chip, minimum flow rate is 250 inverse seconds, and the maximum is 150,000 inverse seconds. And then for the AO5, BO5, CO5 chip series, the minimum shear rate is 40 inverse seconds, and the maximum is 24,000 inverse seconds. And this, again, is completely dependent on the samples that you choose because of this, this relationship here with the pressure sensor 1 or the leading pressure sensor. So this is the pressure sensor that will overpressure first because that will experience the highest pressure along the flow channel. And so long as your pressure of the leading pressure sensor is beneath the maximum pressure of the chip, then you will be able to perform the experiment. And this maximum pressure is really dictated by the viscosity of your sample as well as the shear rate that you use upon your sample. So the combination of these two parameters is what's going to dictate your pressure. So in this equation up here, here this delta P over delta L is just the derivative here. This parameter here is the dimensions of the flow channel, which corresponds to the shear rate. And so the combination of these two is what's going to dictate what pressure range you can experience. So here I have an expression where you can see at the 5% limit, so this is the operational range of the chip, the lower limit is 5% of the maximum pressure. And as for like a safety precaution, we use 95% of the maximum pressure. The instrument itself will prevent you from overpressuring the chip. We have logic in the code that prevents this, but if you're trying to plan out your experiments, this is a good rule of thumb. And so when you multiply your viscosity and your shear rate together and you get your pressure, you can then visualize, okay, is this, I'm using an A-chip, is this combination of a viscosity and shear rate going to be greater than 12,000 pascals? And if so, then the A-chip is inappropriate, but maybe the B-chip is appropriate, and so on and so forth. And you can see if your sample, for instance, with an EO2 chip, if this combination of viscosity and shear rate is beneath the 5% level of 1,800 kilopascals, then you know that your sample and shear rate combination are inappropriate for an EO2 chip. The pressure it generates is too small to be registered accurately on the E-chip itself. And so this brings me to the rate sweep generator spreadsheet that we have internally and that we can share with you, our customers, where here on the right, we have a summary of different chips and what those parameters are. We have a region where you can input your sample information, how much volume you have, the estimated viscosity, and so on and so forth. And then the chip information, so you can put if your B chip has a 40,000 Pascal maximum pressure limit and a minimum of 1,700 Pascals, then you would input that here. We know the channel depth, channel width, and the sensor length, and then the minimum and maximum shear stresses that can be experienced in the chip. And then you can change your maximum flow rate if you wish. And then you can then hit enter, and then it will populate a shear rate sweep for you. And the VROC software also does this, but it's built into the software itself. Microvisc, you have to do this all by hand. Another tool that we provide to you, our customers, is also more of a visualization of a rate sweep. So here we have an A-chip, this visualization for an A-chip. So this purple dotted line here is the minimum 5% full scale of the A-chip. Over here is the maximum. And then this red line is 2 microliters per minute. So on the left-hand side, we have our flow rates. And then on the bottom here, we have our viscosity. And over here is the corresponding shear rate based on this flow rate over here. So the minimum flow rate is 2 microliters per minute. So we can't explore anything down here. So if you have, say, 26 microliters of sample in the Initium 1 Plus, then this region here is what you can explore. So down here to, this is 0.9, 0.8, 0.7, 0.6 centipoise for your samples. You can explore between 100 and 200 microliters per minute. But let's say you have a sample that's 10 centipoise down here. You can explore from 10 microliters per minute flow rate all the way almost to 200 microliters per minute. And this is the full range you can explore. If you have 34 microliters, then this region expands further to from 100 down here all the way up to about 400 microliters per minute. And then if you have more than 50 microliters of sample on the 1 Plus, you can explore the maximum range of the chip. So this whole region here, you can explore. So you can look at the y-axis over here and figure out what viscosities you can explore, and then you can look on the y-axis on the right and see what shear rates you can explore between these two diagonal purple dotted lines. And this, we also have the corresponding flow rates over here. And we have these charts for all of our chips for the 1 Plus. So here's the B05, and you can see limited here by 2 microliters per minute flow rate, and then different sample volumes as well, 26, 34, and then 50. You can explore basically anywhere in the middle here, depending on your sample volume and sample viscosity, as well as the flow rates and corresponding shear rates. And then this holds true for the CO5, and you can see how these diagonal lines have shifted over to the right. So you can't explore as much with the low viscosity fluids as you can with the high viscosity fluids. And then with the EO2 chip, it shifts over just a little bit more from the E02, but now you have much higher shear rates to explore from the corresponding flow rates. And again, you can kind of see clearly how high viscosity samples, you can explore a much wider range of viscosities than you can with the low viscosity fluids, especially if sample volume is the limiting factor here. Because if you say only have 26 microliters and your sample is 2 centipoise, you can't even really measure it. It's above this gray line. But if you had, say, 50 microliters, then you can explore these limited range of shear rates over here. And so that's what happens when you try and plan out these experiments. You can see which chip is optimal for which application. And so that begs the question, what happens if I don't know my sample's viscosity? Well, all of our instruments have what we call automatic mode, where the instrument will decide which shear rate and flow rate to use on your sample based on what chip is inserted into the instrument. And that way, if a sample is inappropriate, such that it's too viscous for that chip, then the instrument will say, oh no, this is an overpressure, we're going to stop the experiment here. So then you know, okay, if I overpressured my A chip with this sample, I need to move to a B chip or a C chip. If the sample is too low in viscosity for your high pressure chips like C and E chips, what will happen is it'll run the experiment, but the data, you'll notice that the data isn't repeatable, or the R-squared values are poor, and that's because the microvisc and the VROC platforms, it'll even show you the percent full scale pressure of the chip that was being used. So if anything is less than 5% full scale, you'll know that it was inappropriate for that particular sample. So you'll still get a number, but the number won't really be accurate. So you'll have to look into the data and you'll see, oh, I need to change from a C chip to a B chip because at this specific viscosity and shear rate, I didn't get enough signal to get an accurate measurement. And so lastly, for my section of the webinar, I have this flow chart on picking the appropriate VROC tool. So if your chip has been, have you selected your chip? No. Determine what chip you want to use. You can play around with it. Let's say a C chip. So you've picked it, yes. Do you know the sample viscosity? No. Run automatic mode and then determine the sample viscosity. And if the sample viscosity is appropriate for your chip, you can then proceed with your shear rate sweep that you want to run, or your temperature sweep at that specific shear rate, and create a protocol based on your specific needs and run your experiment. And that's kind of the general flow that we recommend. Pick a chip, make an accurate or a educated guess on the viscosity if you don't know it, run it on automatic mode to make sure that it can be ran on that specific chip under those settings. And then once you have that viscosity at that one point known, you can then build a rate sweep based on that, or a temperature sweep based on that, and decide which chips you would like to use. And so with that, I'll transfer over to Stacy.
Thanks, Zach. And I'll just make one more quick comment before I start my section. Since Zach has this tool here, this flow chart, I just wanted to point out that the nature of rheology, viscosity included, is there's always, if you're dealing with unknown samples, there tends to be what I'll call an exploratory phase where you're going through a little bit of trial and error to see, to get a feel for the sample before you can get into a full-on defined experiment. So it's not unusual to sort of cycle through some of these steps before you get to the point where you're running your protocols. So it's just the nature of the science. Okay, so the section that I'm going to present today, Zach really focused on our technology, which is the microfluidic technology, but I thought it would be valuable to make an analogy to other common rheometers and viscometers for a couple of reasons. I know that some of the people joining us today might be new to our technology. However, they may have used rotational instruments or capillary tubes in the past. So I thought it might be helpful to, better reinforce what Zach had been discussing by talking about something that's more familiar to them. And the other reason is that a lot of people, when they're new to our technology, think that certain facts about rheology in general are deficiencies of our technology. So by that, I mean, when we're talking to people who have experience in rotational instruments, they'll say, oh, well, your instrument requires us to calculate the viscosity. Our other one measures it directly. Well, that's not true. They all have to be calculated. And the same is true about the tool selection. In general, the other instruments require you to select the appropriate tool to get the best data. So, having to pick the appropriate tool for your sample is not a deficiency of our technology. It's kind of a fact of rheological experimentation. So that is sort of the quick, or maybe not so quick, discussion as to why I wanted to talk about the other, make the analogy to the other types of instrumentation. So I've kind of given away the answer to my question here. The question being, is tool selection, proper tool selection, unique to our particular technology? And the answer is no. Unfortunately, it is not unique to our technology. It's just as important when you're dealing with the other common viscometers and rheometers to choose the right tool for your samples. So what we, as I sort of hinted at, what we're going to do is, in a very broad overview sense, talk about tool selection for the other common style instruments, the one being the rotational rheometers and the other being capillary viscometers. So something like an Capillary tube or Cannon fence or Oswald, I don't know, there's a variety of names that go with the specific designs. And we're going to look at it at a fairly high level. There is more to selecting your tool than we're going to go through, but I think this will still be valuable to get the idea and to make the analogy. With the rotational instruments, it's not just about dimensions, it's also about the specific geometry that you choose, whereas with the capillary viscometers, it is mainly the dimension of the inner radius or inner diameter of the capillary through which the fluid flows. And then it's not just enough to choose the correct tool, you really have to use the tool properly. And so we're going to have sort of a little bonus section at the end where we discuss sort of a common error that people make. And we see this a lot when we do some of our consulting. This is something a common mistake people make when they're new to the field. And it's just sort of a little bonus section where we go through a way of using the tool properly. And then what it will really be focused on is doing these very low shear rate measurements where if you don't use the tools properly, you can generate a lot of poor data. Okay, so let's think about the rotational rheometers and start making the analogy to our microfluidic technology. So as the name implies, the rotational rheometer involves the rotation of a tool about an axis to generate the flow field in the fluid. So we have a couple examples of common tools here: parallel plates, cone and plate, where the fluid is in between the two, is bounded by the two plates, or the cone and the plate, and the tool rotates about the axis to generate the flow field. So unlike our instrumentation where we control flow rate and then measure pressure to calculate shear rate and calculate stress, Now, because of the nature of this experiment, the analogous properties will be angular displacement, so the rotation angle and the rate of rotation, and then the torque. And so the rotational instruments have, there are multiple types, but in general, you're going to control one and measure the other. That's how it works. So you can have controlled strain or you can have controlled stress rheometers, where in controlled strain, angular displacement is controlled, torque is measured, controlled stress, torque is controlled, and angular displacement is monitored. So when you're choosing, so you have to choose the appropriate geometry and dimensions that will work best for your sample. And so we're going to sort of talk about, in a little bit of detail, the common geometries for fluids. And there are some sort of very specific tools that aren't really relevant for this conversation. The main ones related to fluids would be the parallel plates, the cone and plate, and the cup and bob, also referred to as concentric cylinders or the cuvette. And what you're going to be looking to, when you're selecting these tools, you're going to be considering diameter for both the parallel plates and the cone and plate. But then for parallel plates, you're going to have to consider what gap you want to operate at. So what distance between the two plates or fluid height will you be working at? And then for the cone and plate, you need to choose the appropriate cone angle. Gap is fixed based on your angle and your diameter, so you don't have flexibility there, but you do have flexibility a little bit with the angle. And then the cuvette geometries, you can use either double wall or single wall, depending on what is best for your fluid. So we're going to talk a little bit about these. These are the main options. Okay, so what do you want to think about when you're choosing the tools for the rotational rheometer? Well, we already highlighted that one of the important things about the rotational instruments is the torque. And so I'll make another analogy between rotational instruments and our microfluidic instrumentation. So as Zach had explained, for each of our flow channels, there's an operational window for the pressure. And there is the analogous operational window for the torque for the rotational instruments. Now, I'm not going to give numbers here because I'm speaking very generally, because that torque operating window will vary depending on the specific manufacturer and model of your rotational rheometer. So I'm not going to be giving numbers like Zach did. I'm just going to be speaking more in general. But that is the analogy here. There's an operating window for the torque, and you need to choose your tool so that you can, explore as much of that space as you possibly can for your given sample. So that's what you need to keep in mind, is how is my tool selection in combination with my sample going to impact the torque, and what kind of operating window will I have? So that's sort of the very general thought that you want to have when you're trying to choose your tools. And so what you need to realize then is that as you increase the surface area of the tool that's in contact with the fluid, you're going to increase the torque. In addition to the shear stress, or the viscous stress rather, that's generated by the fluid flow, then the other important factor is the surface area. So you have to consider both of those things, the viscous stress that will be generated, which is a function of viscosity and your shear rate, but then also the surface area that's in contact with the fluid. So when you're dealing with, the general rule of thumb then is that when you're dealing with very high viscosity fluids, you want to use a small dimension tool. So a small diameter parallel plate or small diameter cone and plate. And then as your viscosity starts to decrease, now you want to start ramping up the surface area of the tool. So first you'd move then to larger parallel plates or cone and plates. And then as you drop even further in viscosity, and rotational instruments can handle things on viscosity range of, or in viscosity similar to that of water, but you're going to need then to move to the tools with the most surface area, and those would be the concentric cylinders or the cuvette geometries, either the standard one, which is pictured here, or the double wall, which I didn't have the patience to draw. So, but that's the general idea. As you decrease your viscosity, you want to increase your surface area to increase the torque. Because just, I'll just make further emphasize the analogy to our systems. Just like ours, there's a minimum torque range, or sort of a minimum torque as well as a maximum torque. And you can generate data below the minimum torque and it will be poor quality, just like we can do with ours. So you want to avoid that. And then you also want to avoid over torque or overloading the instrument as well. So that's the general rule of thumb. And I want to be a little more, try to emphasize a little more clearly this relationship of the surface area and the viscosity to the torque. So I know this slide violates all etiquette rules of presentation, and math is not the favorite of most people. However, I feel that looking at things in mathematical form can be very helpful. Because it makes very clear how certain parameters relate to other parameters. And so that's really why I put this up here. And I'm just gonna highlight a few things, and then I have the entire derivation here if you want to look at it at a later time, but don't get bogged down by how this looks at the moment. So what I wanted to do, just like we have working equations for our microfluidic flow channels to convert all of the parameters to the viscosity, there are working equations for the rotational tools. And when you look at how these equations come about, I think it really illustrates where this surface area comes in and how it relates to also the viscous nature of the fluid and the stress that generates. I think in math, math really helps me understand things. If this is really not your thing, then you can, skip it. But the idea is that, we have the fluid between the two parallel plates, and we're going to look at the parallel plate geometry because it's fairly straightforward. And as we stated before, we're rotating the tool. And let's just, for the sake of simplicity, talk about, controlling the rate and then measuring the torque. So we're going to control angular velocity and determine what the torque is. Now, what we're going to have to do is we're going to have to, just like we do in our microfluidics, we're going to have to convert this angular velocity to a shear rate, and we're going to have to convert the torque to a shear stress. And then with that, we can calculate the viscosity. So the shear rate comes about pretty easily. Basically, we're just taking the linear velocity, which is r times the angular velocity, r just being the radial position. Here is our coordinate system up here, it's cylindrical coordinates, divided by the gap height. This little rearrangement that we have here and definition of shear rate at the edge is just introduced here because it's used in the derivation where we change variables. Now, what we have to do to get the torque essentially is integrate over the surface of this plate. And so this is where it's very clear where the area of the fluid in contact with the plate becomes important. So our torque is going to be the lever arm, which is the radial position, times the force element. And the force, as we know, is, we can relate force to stress. So stress is force per unit area, so we can then do a change in variables so that we have differential area times the stress. And so if you look at this simple equation here, which is what we need to do to get the total torque to rotate the tool, we see that the torque is proportional to the viscous stress, which depends then on your viscosity and your shear rate, but it's also proportional to the area. So this is where, if you have very high viscous stresses due to, say, a high viscosity fluid, you don't want a large surface area because this will lead to a very high torque and then will lead to the situation where you overload the instrument. So if math is beneficial to you as it is to me, this is sort of a very clear relationship between torque and the viscous stress and the area increment. So the rest of this we don't need to worry too much about. I just don't like to dump equations on people when I don't have to. But basically we're just going to do a little change change of variables in our integral, some rearrangement, apply some rules of integral calculus, and then this leads us to the relationship of the stress to the torque, and also clearly shows you the dependence of the radius of the tool on the stress value. So that's the point I wanted to make. I mean, the real focus is on the top equation, so you can see very clearly the proportionality here and how it impacts the torque. And that what we want to do is choose a tool for our sample such that we can work in as broad of the torque range as possible. And then if you're inclined, you can go in and prove that for Newtonian fluids, this derivative is equal to 1, and we can simplify that stress down to a much simpler equation there. Okay, so hopefully that wasn't too offensive and I was able to make the point. So now what I wanted to do is jump on to capillary tubes. And again, I guess I apologize for the equations. But I think we can quickly move through this. And, again, it's a very similar concept, is you need to choose the right capillary tube for the job. And so if you think about how do you use these capillary tubes, anyone who used them to do intrinsic viscosity knows that although you don't have to use these for intrinsic viscosity, you can use them for just high viscosity fluids as well. They work across the board. But the idea is within the capillary tube, you have a gravity-driven flow through the tube. You have a fluid reservoir here that's, and what's actually dictating the time that the fluid will take to flow is the inner diameter of the capillary portion down here. And what you do is you basically measure the time for the meniscus to move from point C to point D. And you relate this time to the kinematic viscosity. Generally, you'll do both your sample, the sample of importance to you, whether that's, say, a polymer solution when you're doing intrinsic viscosity, or it could be anything else. And generally, then you'd also do a reference sample, which I guess I won't go into too much as to why that is, but oftentimes as you use these and as you clean them, the diameter can change because glass cleaning procedures often will etch a bit of the glass off the tubing, and these change with time. So rather than relying on what the initial diameter was, you would generally deal with a reference fluid. But that's not so important. What's important is that you're getting your kinematic viscosity, which is the ratio of the dynamic viscosity with the density, by looking at this time for the fluid to move between these 2 points. So what you want to choose then is your tube such that this time isn't too short. You don't want it to be too short because then there'll be too much error associated with your measurement. And you don't want it to be too long because you don't want to obviously stand there forever. Although I do understand that there are automated versions of this type of capillary nowadays. So, but even so, in terms of just efficiency, you wouldn't want it to last too long. So again, we're going to look at the working equations of the capillary tube. And these are actually equations, at least the beginning equations are things that we brought up in the past because they have other applications. And again, we're just using these equations because I generally think the mathematics lets you see very clearly the relationship of one parameter to another, and we want to illustrate the importance of the capillary diameter. So we're going to start with the classic law, which we've used in other contexts. So we use this as well when we're talking about injectability, for example. So we're looking at the fluid flow through the cylindrical interior of a needle. Same equation applies, except the difference now is the driving force. So in the injectability discussion, where we start with the same equation, the driving force is the movement of the piston. Now the driving force in this case is gravity. This is gravity-driven flow. So what we're looking at is the volumetric flow rate. So the volume that's being displaced is a function of time. And then this is all related to the basically driving force, which is the pressure drop across a particular length of capillary, the inner radius of the capillary, and the viscosity of the sample that you're measuring. And then the driving force, as we stated, was gravity in this case. And so there's a hydrostatic pressure, which is just density times the gravitational constant times the hydrostatic head is the term that's used, height of the fluid. And so, what we want to do is then get to the equation that we were talking about in the previous slide, where we're relating kinematic viscosity to time. So we rearrange everything. And so we see the kinematic viscosity has this group of parameters proportional to the time. And one of the first things I want to point out then is that if we do a little rearrangement here, we can see the time is going to be inversely proportional to the inner radius to the fourth power. So if your radius, as you shrink your radius down, making it smaller and smaller, then your time will go up. If you make your radius bigger and bigger, then your time will decrease. And so what you want to do is pick the appropriate ratio of the kinematic viscosity to the radius to the fourth power, such that your timing is appropriate. And because it's inconvenient to try to keep track of all of these values for the particular viscometer, generally they simplify this and define this grouping as a viscometer constant. So then we simplify everything quite a bit, just kinematic viscosity times this constant times time. And this constant is actually what you'll look for when you're selecting a particular viscometer. But really what the key thing is the difference in the radius, internal radius of this capillary portion. So what will happen when you go to select your capillary tube is, and I sort of borrowed this table from a brochure that is advertising some of these tubes, Rheology tubes. What you would do is go to the table and look at the viscosity range, find the viscosity range you want to operate in, and then this guides you to a particular tube with a particular viscosity constant, which we just defined, and then it guides you then to select the right viscometer, which they have coded here. So the idea is that's the straightforward process, is that you want to choose your viscometer based on your expected viscosity range. Okay, so with that in mind, we'll finish off with the sort of bonus measurement tip. Again, this is something, as I mentioned, when we consult with people and we see how some of the data is collected at low shear rates on specifically rotational instruments, because rotational instruments will go to lower shear rates than our microfluidics can achieve. We see that there's a common error that occurs, and that is that the measurement time that's chosen is too short. And the reason this is a problem, there are multiple reasons really. One of them is that you have to allow adequate time for the flow profile or the velocity profile to fully develop. In other words, you need to actually get to a steady state. So what you would look for here in this case is the transient curve, so viscosity as a function of time. And this is actually for an experiment for a much higher rate on one of our instruments. But when you're dealing with these extremely low rates, this would be dragged out to minutes or longer. But it makes the point in that what we need to do is get to a plateau and then have enough data on the plateau to get a good amount of averaging. And the averaging is important if you're operating at these very low rates, because if you're operating at very low rates, you're also likely down at the lower end of the torque limit. And so there's more noise, and you want to try to improve things by getting a decent amount of averaging. The other issue that I think people overlook when it comes to this type of measurement at the very low rates and choosing your timing is that in addition to needing to measure long enough to get to steady state, you also have to work within the angular resolution of the instrument. So just like there are torque limitations on the rotational tools, you also have a minimum angular resolution. So there's a particular angular distance you must move for the tool to actually know in an accurate way the rotation that's occurred. So if you're moving at very, very low rates and you don't operate for long enough, then you may very well not achieve this minimum distance that you have to move, this minimum angular distance. And so my apologies again for the equations, but this is a way where you can sort of calculate based on the information that you have regarding your tools and the particular rate that you want to operate. It can guide you as to how long you need to run your experiment. So we're going to sort of look at, again, our parallel plate geometry and what's going to be important. So we've already defined our shear rate at the edge of the tool, because now what we want to look at is, given the time of our measurement and the tool dimensions and the shear rate that we're operating at, how far has the outer edge moved, in what angle, what total angle has this moved in that time? So we solve for the angular velocity, which allows us to, the angular velocity just being the angle increment as a function of time, the derivative of this. So if we integrate and rearrange, we can have an expression for the time it takes to rotate through a particular angle given the properties of the parallel plate and then the shear rate that we want to operate at. Now, the very, very conservative rule of thumb is that you should do a full rotation for your experiment. That's not a problem at all when you're operating at high shear rates. It happens very quickly, so it's not prohibitive in any way. But when you start going down to very low rates, then what I wanted to illustrate is the time goes up quite a bit. So if you take some common dimensions, so fluid depth or fluid distance between the plates, about a 0.5 millimeter, radius of the plates of about 12.5 millimeters, and then a low shear rate value of about 0.01 seconds. So if you go through here and calculate how long would it take to get a full tool rotation, this is going to take on the order of 4 hours. Now, so I point this out because a lot of times we'll see people wanting to do measurements down in this range where they want to do it for a couple of minutes, 1 minute, 2 minutes, and then they want it to be done. But you can see that that is not going to be adequate and not going to give you the best data. Now, when I say that you need to do a full rotation, oftentimes in practice, you can cut this down to half of that or even a quarter of that. You just kind of have to experiment with your system and see what it takes to get quality data there. Again, emphasizing that there's always a little experimental phase when you're doing rheological measurements. But you really want to be cautious when you're doing these low shear rate measurements and make sure you're choosing your parameters properly so you can get the best data. Okay, so I think that's where we'll stop, and we'll open up and look for any questions that any of you may have. And while we wait to see if anyone has questions, I wanted to also just remind everyone, if you're new to our webinars, that if you've signed up for the webinar within a week, you should get a link to the recording and then also the copy of the slides if that's of interest to you. So just bear in mind that if you wanted to review something or re-listen to something, that's an option. You'll get that probably within a week. Okay, so we got our first question. So they're asking about, so this is a question specific to our technology. They're asking about some of our flow channels. And so the question is, for VROC, what is the basic difference between a B10 chip versus a B05 or AO2 versus AO5 as far as pressures and shear rate ranges? So, and you'll be able to, once we send out the slides, you'll be able to go review this so that it's a little more clear. But the difference between a B10 and a B05, they have the same pressure sensors, so the pressure range is equivalent. However, based on the numerical value that follows the letter, they have a different channel depth. So what's the big difference between these is going to be the theoretical shear rate range that they can achieve. And that is also true for the A02 versus the A05. So all A chips have the same pressure sensors, the same pressure range, but in that case, you're looking at a 20 micron versus a 50 micron channel depth. So the theoretical shear rate range is different. Do you have anything else to add?
Just the B05 chip will be able to explore a higher shear rate range than the B10 chip, because the B10 is a 100 micron depth channel, and likewise the A02 chip will be able to achieve higher shear rates than the A05, because again the A02, that 20 micron depth enables us to shear the fluid at higher rates. So that's the key difference between the two channel depths. The smaller the number, the higher the shear rates that can be explored, and the higher the number, the lower shear rates that can be explored.
We'll give it a few more minutes. We'll be patient. So there's another question. How is the VROC Plus different from VROC? So Zach was talking about a lot of his focus, although much of what he said was general, he was choosing flow channels that were available for our Initium instrument, which is our automated instrument. And he had mentioned the Initium, the original, there's the Initium original and there's the Initium 1 Plus. So the 1 Plus is the new automated model, which has some modifications so that it can handle not just aqueous systems, but organic-based systems. Because in the past, the old instrument, some of the components were sensitive to organic solvents, and in actuality, it was really designed to mainly handle aqueous systems. So 1 Plus is the new automated model, which is expanded to organic solvents. Okay, so there's a comment talking about if you're trying to do a shear rate sweep starting at 0.0001 inverse seconds on a rotational instrument, and the question is, this will take forever to get reliable data, and I would agree that it's going to take a long time to get reliable data. Will you need an entire rotation of the tool? Maybe not. You might be able to scale it back to, like I said, a half or quarter rotation. So you may be able to save some time there, but you will have to put time in there. You're not going to be able to get that measurement very quickly. It's just the nature of the experiment. The same is true if you're familiar with rotational instruments and you're doing oscillatory or dynamic experiments. You know that when you go down to low frequencies, those also take much longer to achieve. It's just kind of the nature of the game. So you can take the equations that we presented, I guess, on the final slide there. I haven't calculated for 0.0001, but what you want to do is take that value and then also the other parameters of your tool. So if you're using, for example, parallel plates, you want to get the radius and then also the gap that you're using, and then you could use those equations to basically estimate how long it would take to go, say, a quarter of a rotation, half rotation, full rotation, and then you could try those out. But yes, it will take time. So the next question is asking about our instrumentation and shear rate sweep. So the question is, when you run a shear rate sweep on our device, is it going to have variable force, and is it going to take a long time to get reliable data for low shear rates? So I'm not sure what you mean by variable force. Maybe if you could clarify that, but in terms of how long is it going to take? So our instrument is similar in the fact that, as we go to lower and lower rates, we do have to allow longer and longer times to reach steady state. We don't have to worry about the angular resolution problem, but we still do have to allow extra time to ramp up to a steady state or fully developed velocity profile. So yes, our measurements at lower shear rates take longer than our measurements at high shear rates. So that analogy holds up. But we can't go to 0.001 inverse seconds. So we're never going to have measurements that long.
I think the longest I've had to wait for a single shear rate at a very low shear rate, less than 100 inverse seconds, is on the order of like 5 minutes,
Okay.
5-10 minutes total.
Yeah, but we're not getting anywhere near 0.001.
Yeah.
Okay, so there's clarification on the question. So I think the actual question was, when you run shear rate sweeps on our device, is it going to have variable speed? And yes, so if you have a particular flow channel, then your channel depth is fixed, and so the way you would vary your shear rate is by changing the flow rate or the velocity of the fluid through the flow channel. So yes, hopefully that answers that. Hopefully I understood that properly. For a fixed flow channel depth, you will adjust shear rate by adjusting the volumetric flow rate or the velocity of the fluid. Okay. So I think we've gone an hour, and I think we've got all the questions that are coming in. So thank you again for joining us, and we will be back in December with another webinar, so please join again.
Thank you.